All right, so we're going to be starting a series of physiology lectures, and the first few modules will focus on some of the core topics in respiratory mechanics. So the first one here today, we'll talk about the pressures of the respiratory system with a special emphasis on transpulmonary pressure. So objectives of this module are we'll try to introduce the single compartment model of the respiratory system. We'll understand the concept of transmural pressure. We'll understand the nomenclature and definitions of the various pressures of the respiratory system, and have a deeper understanding of the physiological meaning and importance of transpulmonary pressure. So this is a sample case to start. We have a 35-year-old male, history of with a BMI of 68, who develops ARDS. He's ventilated with the FiO2 of 100%, PEEP of 20, plateau is 32, and the P to F ratio is 50. And esophageal balloon is placed, and the end expiratory esophageal pressure is 24. The only question is, how can you use this information to set PEEP in this patient? And this is another poll to just kind of think about as we're talking about this. How would you define transpulmonary pressure? Is it alveolar pressure minus pleural pressure? Is it airway pressure minus pleural pressure? Is it airway pressure minus alveolar pressure, or none of the above? And another question is, which of the following pressures is directly transmitted to the pericardial pressure? Is it airway pressure, alveolar pressure, pleural pressure, or transpulmonary pressure? And we'll try to answer some of these questions today. So to have a coherent discussion about respiratory mechanics, we have to first start by modeling the respiratory system. And one of the popular models we use is the single compartment model. Now, in this model, we assume there is a single compartment within the respiratory system. In other words, every single airway is represented by a single airway, and all alveoli are represented by a single alveolus in this model. So again, this particular airway right here represents every single airway in the respiratory system, and all the way from trachea down to the terminal bronchioles. And this alveolus represents all alveoli, or in other words, the lung parenchyma. And this is surrounded by the chest wall. So this is our single compartment model. So there are these two cardinal properties of the respiratory system that we use to describe the mechanics. The first one is the resistance of the respiratory system, and the second one is the elastance, which in simple English means stiffness, or the compliance, which is the inverse of elastance of the respiratory system. The resistance occurs whenever there is airflow. So whenever there's flow, there has to be certain friction against which the flow occurs, and this friction results in the resistance of the respiratory system. And the elastance or stiffness is the second property, which basically, again, depends on how stiff an expanding structure is. So we'll try to define these two properties of the respiratory system. The key assumptions of this model are that the airway is non-distensible. So the airway is, you can imagine the airway being like a lead pipe, which does not distend at all. It has infinite elasticity for the purpose of this model. So the airway only serves as a conduit for gas flow from the airway opening into the alveolus and the chest wall. So in being a conduit, then the airway is hence responsible for resistance to airflow. So all the airway is doing in this model is it's allowing passage for airflow from the atmosphere, or the ventilator, for example, down into the lower compartments, which is the alveoli and the chest wall. So as the air flows through the airways, the friction that's created causes resistance to the airflow. So in this sense, the airways are responsible for the resistance to the airflow. So as the alveoli are in this model, a single alveolus plus the chest wall receive the airflow flowing from the airway, they expand, and depending on their properties of how stiff the alveolus and the chest wall is, they are hence responsible for the elastance of the respiratory system. So to summarize, airway is responsible for resistance, and the combination of alveolus plus chest wall are responsible for elastance of the respiratory system. And this is again represented here. You have the single compartment model, airway on the top, and alveolus surrounded by chest wall in the bottom. The airway is the resistive component, also known as dynamic component, because airflow is a dynamic phenomenon, and the components down in the alveolus and the chest wall, these are elastic components. We also call them static components because this pertains to static expansion and not necessarily airflow.
So a key point in terminology before I move forward is that in respiratory mechanics, the word lung refers to airway and parenchyma. So all this white here, this is all lung. So whenever we talk about pressure across the lung or anything to do with lung, just think about the white stuff. So the airway and the alveolus together comprise of the lung. So, and this is the pore pressure. All right, so, trying to define pressure. So it's an useful reminder that pressure is force divided by area. So, essentially pressure can be thought of as force. And we already talked about this. In medicine, we talk about pressures. These are pressures relative to atmospheric pressures. So negative pressure means that the pressure is lower than atmospheric pressure, which creates a suction effect. A positive pressure means that the pressure is higher than atmospheric pressure. And if we say a pressure is 0, which means that it is atmospheric pressure. For example, when we say we are on sea level, blood pressure is 120/80, what we actually mean in terms of physical terms is that the pressure is 880/840. However, in Mexico City, their atmospheric pressure is 570, so the same blood pressure would be 690/650. All right, now this is an important concept, so the concept of transmural pressure, which pertains to not only pulmonary physiology, but also extremely relevant in cardiovascular physiology, so we have to understand this. So the word mural it means wall, and so transmural means across the wall. So let's think of an air-filled balloon that's placed in a pressure chamber. So pressure inside the balloon, we can call it intramural pressure. The pressure outside, extramural, and the pressure across is the transmural pressure. So we can, this is the pressure gradient between inside and outside the chamber. So mathematically, obviously, the transmural pressure would be the difference between intramural and extramural pressure. And here's a graphical representation of that. So this is any distensible chamber, for example, a balloon or an alveolus. So the pressure inside is intramural pressure. Pressure outside is extramural pressure. And the transmural pressure across the wall of this chamber is the difference between the two. Now, why is this important? Because it's the transmural pressure that's the actual distending pressure of this chamber, and hence determines wall stress, like how much stress the wall of this chamber is feeling. So let's just stick with the balloon analogy. So in resting state, the balloon is completely deflated, right? So at this point, pressure inside equals pressure outside, and there's no stress on the wall. And because the pressure inside equals pressure outside, the transmural pressure is 0, so the wall stress is 0. Now we start blowing up the balloon. So the pressure inside the balloon now starts becoming higher than the pressure outside. So mathematically, this means the transmural pressure starts becoming positive. And now wall stress is present and would be proportional to the degree of inflation. And the key point here is that it's the higher the transmural pressure, higher would be the degree of inflation, and higher would be the wall stress. So let's watch this video, and that'll illustrate a point. And let me know if you can't hear the audio.
Hello, I'm Jared, back with another experiment on air pressure. And this one's so simple, that's the beauty of it. I have a juice bottle. This is just a small little apple juice bottle. I picked the juice bottles because the plastic is thicker. A balloon, and that's really all you need. This piece of paper is just to help the camera pick up something. So what I need to do is to prep the bottle. So I have to actually cut a little hole in the bottle, and I'm going to hold this up, point to the hole, and hopefully you can see it. I ringed it with a little black marker there. That hole is important. And I'm going to insert the balloon and stretch it over the top. Because the top is a little large, you might have a little difficulty, but that's it. I'm ready to go. So where's the magic? Well, but what's cool about air pressure is I can get the air in this room to blow up this balloon by removing the air inside the bottle. So how do I do that? Well, I'm going to suck it out. I can actually blow up a balloon by sucking, by inhaling. It blows my mind just thinking about it. So this might look a little strange and odd to the camera, but I'm actually going to put my mouth over this hole and suck in a short, quick burst. It's weird, but check out what happens. You'll see the balloon inflate because the pressure in the room is actually going from high to low pressure. And now I put my finger over the hole, and the balloon, check this out. There's nothing blocking this. It's wide open, but the balloon stays inflated. That blows my mind. Think about that. Why? Because all the pressure in this room is greater than the pressure inside that bottle. So it's pushing down inside the balloon because there's no pressure inside the bottle pushing it back. As soon as I add pressure into the bottle, it's going to force the air back out because the pressure is going to equalize. So watch. The air rushed in, pressure equalized. You can blow up a balloon by sucking in. Science is cool. Thanks for watching.
So someone explained to me this in terms of transmural pressure. So what changes occurred when he did this experiment in terms of intramural, extramural, transmural pressure? Anyone? In the balloon, I mean. So what happened to the pressure around the balloon when he was sucking air into the bottom from the bottom?
I can try. I'm
Okay,
probably, but let's think about this. So the pressure around the balloon decreased, but the pressure on the inside of the balloon stayed the same because it's the same as atmospheric pressure. So
zero.
a negative number minus 0. So the transmural pressure increased, which led to expansion and inflation of the balloon.
Spot on. Spot on. So this is exactly what happens. So the point is, if we were to put a catheter inside the balloon at this point, it's 0, because I mean it's obvious because the balloon opening is open to the atmosphere, right? So the reason the balloon is expanding is the pressure outside the balloon, the extramural pressure is going down. And this guy's obviously fascinated. I'm not, because I understand how we breathe. This is how all of us breathe. This is how spontaneous negative pressure ventilation works. We expand our chest, the air goes in from the mouth, and the lungs expand. So this is key to understand because this is going to be relevant for both cardiovascular and pulmonary physiology. So awesome. Thanks, Maria. All right, so the concept of transmural pressure. So the key point is it doesn't matter how a particular transmural pressure is generated. So you can increase the transmural pressure by increasing the intramural pressure. For example, if we blow into the balloon, right? So we're creating positive pressure inside the balloon. Or you can reduce the extramural pressure like we did in that experiment. So a particular transmural pressure will result in the same degree of inflation and the same wall stress in a particular object. Now, in other words, say, for example, the guy in the experiment blew up the balloon so that the balloon had 50 cc of air in it, just a random number. If I was to pump in 50 cc of air in the balloon, the degree of stress on the wall of the balloon would be absolutely identical to this experiment. So it doesn't matter how you create the transmural pressure. What matters is what the transmural pressure is. All right, any questions? Because this is probably the most important part of today. All right. So these are some of the pressures we're going to be talking about. There are pressures at specific locations in the respiratory system, and there are pressures across various locations. And I won't go listing these right now because we're going to be talking about this in a second. And just to highlight that the last two of these are actually transmural pressure, which is the concept we just talked about. All right, so we're going to use this as our guide trying to understand these pressures. Now, right off the bat, can anyone tell me in this model, when you see a pressure reading on the ventilator, someone's intubated, connected to a mechanical ventilator, and the vent tells you the airway pressure is going up and down, so and so, and it's whatever X number. So where is that being measured by the ventilator? Any takers?
The Y.
Absolutely. So the Y, which means the in other words, the airway opening, right, Ahmed? So it's right here in this model where my cursor is. We call this the airway pressure, PAW, or airway opening pressures, PAO. Now, when we're spontaneously breathing, the Y, we don't have a ventilator. The Y essentially is our mouth opening, so which is exposed to the atmosphere, right? So in spontaneous breathing, the airway opening pressure is 0. But when someone is getting positive pressure ventilation, when the machine's pushing air into someone, the pressure that's being measured is at the airway opening, which is going to be positive. All right, that's the first one. And this is essentially a P-vent when we talk about equation of motion, which is a separate issue. All right, so the second pressure is in the alveolus. Any examples of what that might be in clinical practice? For the sake of time, I'll mention that. It's plateau. Sorry. What were you going to say?
The plateau pressure that you just said.
There you go. Yep, I heard you. All right, so plateau pressure is alveolar pressure, correct. So plateau pressure is and inspiratory alveolar pressure. Whereas if you think about it, PEEP, when you're actually measuring PEEP, and it is an expiratory alveolar pressure. So the third pressure is the pleural pressure. This is simple to understand, right? It's the pressure in the pleural space right outside the lungs and within the chest wall. And the fourth one is body surface pressure. Now, we don't use this a lot. However, this is pressure outside the body, which is atmospheric pressure, because unless we are in a negative pressure chamber, this should be equal to 0, which is atmospheric pressure. These are the 4 pressures out of the 8. I think these are all easy to understand. So airway opening pressure, alveolar pressure, pleural pressure, body surface pressure.
Can I just clarify one just terminology, Aman?
Yeah.
In number one, where you say the airway pressure, actually, I would change the way that you're displaying that, because it's not airway opening pressure, it's at the airway opening, which can be misunderstood as at the pressure at which the airways open up, which has to do with PEEP recruitment pressure and terminal pressure. Does that make sense?
Yeah, so you would say change it to what, sorry?
PAO,
yeah.
The pressure is pressure at the airway opening, not airway opening pressures, which is a different statement. Does that make sense?
Okay. Yes, pressure at the airway opening. Right.
Yeah, thank you.
Yep. All right, so the pleural pressure is kind of important. It's a pressure in the pleural space. Now, if you ask someone what's the pleural pressure in a given patient, the answer would be depends on where you measure it, because there's no single value of pleural pressure because gravity plays a role. So what happens is, lung and mediastinal structures such as heart, they have weight, and because they have weight, they exert gravity on the dependent portions of the thoracic cavity. So this is why there's a vertical pressure gradient. So the pleural pressure is the highest in the dependent, which means lower regions, and then it's the lowest in the non-dependent regions. And this is purely because of the effect of gravity. So and this gradient is accentuated in ARDS. This is a cartoon that helps kind of clarify that. This is a person who's standing upright. You can see that in the most non-dependent regions up here, the pleural pressure is lowest. It's kind of in the middle regions, and in the most dependent regions, because these regions are feeling the weight of the structures above it. If you measure the pleural pressure here, it'll be -3, which is higher than the non-dependent regions. And it ties in heart-lung physiology, and this is the answer to the second question that I asked. Is this pleural pressure is directly transmitted to pericardial pressure, and therefore changes in pleural pressure have direct hemodynamic effects. So if there's one pressure that has direct hemodynamic consequences, that's pleural pressure. And we'll learn more about that in cardiovascular physiology, its effect on the right heart and the left heart. All right, so half the battle's done. We've discussed pressures at specific locations. Now we're going to talk about pressures across specific locations. So, and this is, a good, kind of standard terminology that we used in our SEVA module, which we'll try to stick to. So back to our single compartment model, which we've already defined these 4 pressures. So these are pressures at locations. So we're going to have now define pressures across locations. So how do we do that? Well, we will name the pressures across these 4 locations. So from 1 to 2, 2 to 3, 3 to 4, that's easy to understand. Then finally, we'll do something different, and we'll do 1 to 3. So let's do that. So 1 to 2 is the pressure between airway opening and alveolar pressure. This pressure gradient is trans-airway pressure. The pressure between 2 to 3, so the alveolar pressure minus the pleural pressure, is the transalveolar pressure. And this, like I said, is a transmural pressure. Pressure between 3 to 4, which means pleural pressure minus the body surface pressure, which is typically 0, is the trans-chest wall pressure. It's the pressure across the chest wall. And then these are all contiguous, so easy to understand. The fourth one is a little bit tricky. So it's between 1 and 3. So airway pressure and pleural pressure. And this we call the transpulmonary pressure, because remember, when we talk about mechanics, the lung is both airways and the lung parenchyma. So the pressure across both airways and lung parenchyma is transpulmonary pressure. And we'll talk about all of these individually, but this is just to highlight the terminology. So we'll talk about this one by one. First is trans-airway pressure. So that is right here, airway pressure minus alveolar pressure. Now, what's the significance of this? It's airway pressure minus alveolar pressure. Now, I already mentioned that this pressure will exist only in the presence of airflow. If there's no, because essentially what this is representing is the resistive pressure drop across the airways. So I already mentioned that airways represent the resistive component of our model. And if there is no airflow, there will be no friction, there will be no resistive pressure. So this pressure difference would be 0. So the clinical coordinate of this is, if you're talking about mechanical ventilation, then remember that the ventilator always measures pressure at the airway opening. So if we want to kind of estimate alveolar pressure, which like Marina said is the plateau, for example, how can we do that on the ventilator? Well, it's simple. You stop the airflow. You stop the airflow, there's no trans-airway pressure, then your reading on the ventilator at the airway opening would reflect the reading in the alveolus. So in the absence of airflow, airway pressure equals alveolar pressure. And this is how we measure plateau pressure and then total PEEP. And in these situations, pressure measured by the ventilator at the airway opening reflect alveolar pressure. The second one is transalveolar pressure. So this one is right here. So it's alveolar pressure minus pleural pressure. This is particularly important for us. So it's alveolar pressure minus pleural pressure. And this is the transmural pressure, like I mentioned. So the alveolar pressure is similar to the balloon. It's intramural pressure. The pressure outside the alveolus is extramural, which is the pleural pressure. And so the alveolar pressure is actually a transmural pressure. This particular pressure is so important. So this is the true distending pressure of the alveolus, not the alveolar pressure itself. And this would make sense because alveolar filling increases proportionally as we increase the transalveolar pressure. And this is also a true measure of alveolar stress, which is a factor pertinent to ventilation-induced lung injury. So this is kind of the graphical representation of this. So if on the x-axis you have transalveolar pressure, and on the y-axis you have the alveolar volume. As we increase the transalveolar pressure, the alveolar volume is going to go up, similar to the balloon, until when you have very high volume, then the alveolus stiffens up, and any further increase in pressure doesn't really cause a lot of increase in volume. So the clinical correlates are, so plateau and PEEP are reflections of alveolar pressure because technically they are airway opening pressures, but in the absence of airflow, they reflect alveolar pressures. But they don't actually reflect alveolar stress because you have to take the pleural pressure into account to actually determine alveolar stress. So in other words, you need to know the transalveolar pressure to actually determine alveolar stress. So what we have to do is we have to subtract pleural pressure from plateau pressure and PEEP to determine the actual lung stress. And this is a clinical example. In trumpet players, the alveolar pressure can go up to 150 because they're forcefully exhaling so much that their expiratory muscles are pushing on the chest wall. But so why don't they get a pneumothorax? Because, well, they're pushing on the chest wall, so the pleural pressure is also very high. So in this typical example, the transalveolar pressure is only 10, even though if you were to put a catheter in the alveolus, which is not practical to do, your alveolar pressure would be 150. But like I mentioned several times, it's the transalveolar pressure that matters. And in this case, it's not that high. It's only 10. All right, the third one is pretty brief. It's the trans-chest wall pressure right here. Not very pertinent for today's talk. We'll have a separate module on chest wall mechanics. So essentially, this is pleural pressure minus body surface pressure, which is typically 0 in a relaxed chest wall with no PMUS. And this will become important when we talk about chest wall mechanics, so I'm just going to skip it for now. And finally, number 4, we have transpulmonary pressure now. This was the one where we had to do 1 minus 3, remember? It's the pressure across the entire lung, so airway plus parenchyma, right here. So airway pressure minus pleural pressure, that's your transpulmonary pressure. So the definition of this is the pressure across the lung. And this is the sum of airway pressure and transalveolar pressure. So it's the sum of this pressure right here and the pressure difference between alveolus and the pleural pressure. This is important to mention because a lot of us kind of equate transpulmonary pressure to transalveolar pressure. And, strictly speaking, that's not true, and sometimes that causes confusion. So in the absence of airflow, like I already mentioned, the transairway pressure is 0. So in the absence of airflow, it is true to say that transpulmonary pressure is transalveolar pressure. And this is how we can use transpulmonary pressure to more accurately estimate lung stress. So clinically, how can we use this? So clinically, if we have esophageal balloon, we can do 2 things. So we already know how to measure plateau and PEEP, right? All we need to know is pleural pressure. We can estimate that with the esophageal balloon. So when we check the pleural pressure at end inspiration, like we check plateau pressure, that we can use this, and we can then calculate plateau minus end inspiratory pleural pressure. That would reflect inspiratory lung stress. The same thing if we check the end expiratory pleural pressure and we do PEEP minus end expiratory pleural pressure, that value would reflect expiratory lung stress. So any questions so far? And we may not have time to go over clinical correlates, but I want to make sure that whatever we discussed so far has registered.
Well, one of the questions obviously is when you use the term stress. What do you mean by that, Aman? Right.
So, in terms of material science, I think we borrowed that term from material science. So they have this terms called stress and strain. If you're exerting pressure on an elastic structure, the tension kind of felt by that elastic structure is probably called stress, and the degree of stretch is called strain. So I think that's what we borrow these terms, stress and strain from material science. But in this case, we're basically kind of using the pressure itself as a reflection of the stress that the alveolus is feeling.
Yeah, I think that this is important because sometimes there are two different characteristics of what the alveoli sees. In stress is what the alveolar pressure exists at that given moment, and so which may have different effects or different thresholds that strain or the amount of distension that the alveoli has. And so in times we use these terms, and as clinical application at the bedside can be difficult to understand what each one means. The other one that so there's more to come, but I think that you have explained it very nice. The second question I had for you, you said that in terms of hemodynamic statements, and if you're going to cover these later, you can do so, but you said that the one that mattered was the pleural pressure.
Right.
I wanted you to comment a little bit regarding in terms of stress of the alveolar wall and flow of blood that the alveoli will have and its effect on perfusion, RV strain, and whatnot. So if you're going to comment about that, because I don't want them to leave with the thought that it's just the pleural pressure, that there's other things through this. Go ahead.
Yes, I would rectify my statement saying that it is, so I would probably addend it. So certainly what I meant by that is the pleural pressure would add directly to the pericardial pressure, so the pressure around the heart. So it'll be hemodynamically significant in that sense if you just focus on the pressures of the heart. But you're right, what you're saying is, if you have alveolar overinflation, then you can increase your pulmonary vascular resistance. So that would also obviously have hemodynamic consequences, and that would occur, that would be proportional to your transalveolar pressure or your, end respiratory transpulmonary pressure. So yeah, so I would addend that, these pressures are also important, but that was partly correct, in other words. And we'll talk about all of that, in other modules.